Yes. Okay. In the classes, there are different things going on. Where can I find it? Mayor's theorem and cluster expansion. He said his own book, but that is not available in the online. Yes, but they are too early. These things are already have done. In the Macquarie book, they are not available. No, no. Can you please give it? I am getting these things very tough. Cluster expansion and math theory. Ordered parameter. These things.
it's basically a different course. It's not core course of statistical mechanics. Okay, Landau theory, Ising model, Pairs theory, phase transition. These things are there. BCE, BC. Sorry, these things are from statistical mechanics. I agree, but these are not the core main basic things. These are the advanced topics to discuss. So if you want, I can discuss mass theory that I will do next class if you want. But I have to also read those things. I'm not very well known about those things. But Landau theory I know a little bit. Landau theory and the other things that I know. But my work or this mass theory also I don't know very much. Main thing I know it is cluster expansion I don't know. Because cluster expansion these things were needed for computational chemistry or physics. Okay. Because they have to deal with lots of molecules, lots of things. Now, so in those cases, they actually need these theories actually. But for our cases, in the field we are doing, in those cases, these things are not very much important because we don't beyond our molecular microscopic level and nano scale actually microscopic level. Yeah. Means we deal with the atomic scale, but if you want to deal with more than one, hydrogen, you can solve the Schrodinger equation for hydrogen atom only, right? When you
Yes.
want to deal with molecules, lots of molecules, you want to simulate some reaction, something, some physical transition, phase transition. For those cases, you have to basically then you apply these theories. Otherwise, these are basically the approximation like things. Then only you can do. Okay? If you want, you can study, learn it. Then I have to also see some videos of these lectures. Then I will discuss in class. Okay, that I can do. And the difference, I think the Bhaktisar book is good for this. You can find these things. Or okay, I will search for references. Okay, then if I got, I will send.
This book is available on the library.
Library में तो available है. Library in library it's available. In but in online I don't know. Means library I can get only the PDF version. Sorry, the hard copy, not the PDF version. That's the
In
thing.
the National Digital Library.
So that I'm not saying. I'm saying in our institute library. In our institute library in IIT Kanpur, there is a library in IIT University. So in your university also there must be library, right?
Yes, but it said that there was not any in any course structure about our university. It was there, so these things are not in our library.
These books are not there.
No, because it is important in the point of view of physics, not for chemistry.
They said this.
Yes,
So
cluster expansion and these things they are not.
physics chemistry library should be a general body, na?
Yes, but in physics there is also not available.
Okay.
In the MSc syllabus of Bador University, this is not available.
Okay. Okay, let me find out. Okay, I will get it. Don't worry. Otherwise, I have to arrange this because I know even by the students, they definitely has this book.
Okay, so please send me this.
Then I will. But do you want to discuss these things? Because do you find these things related to your interest? Then I will discuss. Otherwise, I don't want to get into this because these things are very difficult. If not difficult, this will we have to pay a lot of involvement into these things. Then today we will discuss the grand canonical part. This part will be covered. Don't worry. Means okay, this part will be covered. But next we can do things. One thing is discussing these things, Bayes theory, Landau theory, these things, Ising model, or we can discuss the other statistical mechanics part, this microscopic translational, rotational, vibrational, specific in, space transition, these things that we have to select.
The questions will be from both the part, this mass theory and these things.
I can't hear it.
In the exam, the questions will be come from both sides, from this math side and also the statistical side.
Okay, in exam I don't know because I have in exam means which exam? Exam for this course
Yes,
probably because do you have seen the assignment question?
yes,
So in assignment questions are from there as well.
yes. Some order parameter question I am able to solve because they are first derivative equal to zero. Such things.
Okay, okay. So then it's better to discuss those things as well. So one thing you can do. Uh, first you just send me the assignment question. I can also download that, but you can send me. I will see the assignment question, and it's better to discuss this maths theory and these things because
From this week, after week 5.
after
After week 5, I will send the assignment question from week 1.
because we don't have discussed this assignment question, right?
Yes,
So it's better to discuss those as well in one class. Okay, let's plan according to this. Before this class, week 6 or week 5, then we'll discuss this maths theory and this part because we have 4 classes. If you consider today's class, week 7, and in next class, if we discuss the question answer, then we will have 4 more classes. Then in those classes we can discuss easily, I think, right?
yes,
Okay, so then because I need also some time to prepare these things, that's why I'm saying. Okay,
okay,
okay. So then yes, I'll find the references according to those books. Okay, in lectures I have not gone through the lectures because I was following the this week topics covered in that week, okay, in the written format which is available in the NPTEL website. According to that I was going. I did not expect that he is not following that order, but these should be written according to the week lectures. How they have written this then? I don't know.
yes,
It should not be like this. Okay, then I have to watch those videos as well. Because you see, Grand Canonical Ensemble is in week 6,
yes. But they are already covered.
already covered. And you are saying those mayors are in the week 10.
Yes,
These things covered? Ideal monatomic gas, translational, rotational,
yes.
vibrational. These things are
Only,
also
only,
covered.
only translational is covered. The rotational vibrational will be covered in next class.
Okay, I don't know. Ising model?
Now it's going on these
Okay,
things.
okay, okay, okay. Then this is probably today's week 7, right?
Yes,
Okay, then today I am completing this grand canonical part. Today I will discuss totally this, and then in next week we will do the question answer, and then totally this advanced statistical, you can say. Okay, then I think it will okay.
okay,
These things will not require more than 2 class because we will not get into very detail. In 2 class, it will 2 classes it will be okay. So 7, 8, 9, 10. Yes, and rest of 2 class we will discuss these rotational vibrational ones. 11 and for last class we'll see what we can do. Okay.
okay.
Okay, so let me share my screen.
The screen is not visible.
Screen is not visible.
Yes.
Now visible, right?
No.
It is not visible. Oh my God. Let me check. You can see the screen now.
Yes.
Now,
Yes, visible.
okay. In last class, we have derived the expression for the partition function for grand canonical ensemble, right? Do you have done these things by your own hand? You would. Then it will give you the feelings. This is the partition function for grand canonical ensemble. You can see we have just have extra one more term, this term. This was missing in case of canonical ensemble. In grand canonical one, this number term, because a number is not also fixed. So this term will be there. And this is the probability of having a particle in the kj level. Kj means kth energy, kth particle, and jth energy level, right? Because now energy
Yes.
levels are like there are jth energy levels, and each energy levels there are lots of kth part number level, right? Particle number levels like that.
Yes.
So okay, so today we'll see the thermodynamic connections. These things are not difficult, I would say, because these things you have already done in canonical ensemble, but you have to be more cautious because now one more extra term is there, right? So it may be uh, it is very prone to be mistake actually because you will see you have to deal with lots of derivatives. These things are there, so it's very common to do some mistakes. So we have to be very careful, right? So let us start. Just see, probably if I have done some mistake, you should mention it. Otherwise, it will be okay. So first, what to calculate the internal energy. Mm. Internal energy is function of what?
Temperature and volume.
This stand canonical. This is grand canonical. You have to keep in mind. So yes, you are right. V, beta, and
Mu and T.
gamma. No, you don't
Yes.
know. Till now, you don't know beta is related to temperature and gamma is related to chemical potential. You don't know this. This we will see later.
We have proved it in the last week.
No, that is for canonical,
Yes.
not for grand canonical. So what should be the formula for this average? You know, for any average, you have to just uh, multiply with the probability.
EJ, PJ.
KJ, right?
For
PKJ
grand
and
canonical, it's KJ.
for grand canonical, yes. And this is gamma, beta, B again. And you have to take sum over K, sum over J. As simple as that. It's just straightforward. Then we will put the form of our PKJ, sorry. Sometimes you can see it can be written like this in books, right? KJ for shorthand notation. Okay,
Both are same.
same. So what is PKJ now? PKJ is e to the power minus beta EKJ. EKJ was function of only V, e to the power minus gamma, not EKJ, I think EJ. Yes, EJ NQ. And divided by our partition function, right? Grand
Yes.
canonical partition function. Grand canonical partition function is also function. So do you know what is this sign?
Summation.
No, no, not something.
Then I don't know.
This is xi. This is xi, na?
What is its significance?
This is a notation, big letter, partition function,
This is big Xi.
big xi. I don't know why they have chosen this complicated notation like that. I don't know. And you know the form of this. This is
Sum over K, sum over J, e to the power minus beta.
now you say what should we do to find out this internal energy or the average. How should we proceed now? You know the canonical part. What we have done there?
By
We have
taking the log.
taken the log, but we have done first derivative of that partition function. You see, del q del beta was there. And after doing derivative, we will find that that was equals to this e to the power term, and we have just replaced this, right? If you remember
Yes.
that here, same thing we will do here because we will follow the same tricks and we'll see whether that works or not. Otherwise, we have to do different thing. Okay. So you see, this is the numerator. No, this is not the numerator because this is EJ. Oh, and it should be also the EJ because we have introduced the sum and this is the total, right? This is the average, so this should be the EJ, sorry. So this is the numerator. And when you have write this, EJ is not function of V and beta. So this is mistake actually, sorry. E is function of Y is function of V and beta because beta is coming from here and gamma is coming from here. And EJ is the function of V only. Okay. This we have to keep in mind. Is it clear?
Okay.
Just remember the canonical part. It was function of N and V and N and V, but it was function of N, V and beta. Beta was coming from here. Correct? So
In
same
grand
thing.
canonical, this energy is also dependent on the number.
No. No, number is not
In
now
every
a
state,
constant
there is
thing.
change in number.
What you have to say? Repeat it.
The number is changing in various energy states.
Then energy state will also be changed now. EJ.
Yes, so energy will be function of volume and number also.
No, no, no. That's why we have additionally added one state. That will be a different state now. Because if you remember EJ, under this EJ now these states are there. EJ1,
Yes,
EJ2, this number. So that's why this we have treated as a different state right now. Okay, that's the reason. In
okay.
canonical, if you remember, N was fixed. Okay, canonical
Yes,
say in canonical ensemble, don't confuse these two things. These variables, beta, gamma, these variables are for different microstates. That's okay. But V is not varying. Just see here, V is not varying for the microstate. For all microstate, V is same. But still, why you have written
yes,
EJ is function of V? Because if you choose a different V, it will be a different ensemble, right? Different grand canonical ensemble. That is important. That EJ is function of V, that is not due to taking lots of copies. No, V is same for all copies. But from the beginning, if we start with the different V, then it will be a different energy distribution, not the same. It means that, okay. So in canonical
for
ensemble,
same chemical ensemble, volume is fixed.
huh, for all copies, it's for canonical ensemble for all copies, N and V both are fixed. NVT was same now for all copies. Here for
Yes,
mu VT, all are same now. That's why. That's why. In
mu vt is
canonical,
constant.
for all copies, in grand canonical. Here we can see it is beta mu and beta gamma and V. Later we'll see beta is actually temperature and gamma is actually chemical temperature.
Yes,
In that way. So in canonical ensemble, number is fixed for all copies. But EJ is function of N and V. That means that distribution will change if you start with a different number. That is the reason of that N. That does not mean that all microscopic state microstate N is changing. No, in canonical ensemble N is not changing. But EJ is function of N. So that is the reason. EJ means the distribution, canonical ensemble distribution. Correct? EJ has that essence of that distribution, infinite number of copies. So again, you can't put that. EJ will be function of those things which is predetermined, which is constant for that ensemble. Okay?
yes,
Because after taking those constant N or V something, then you have defined those copies and you have got those distribution of EJ. That is important. So don't confuse these two things. Okay. Now, if this is the case, then this is the numerator. You can easily figure it out. So from here, you can write it. What should be our E average now? This is minus this. Okay. Okay. Next, what should we do? Pressure, right?
network was gone, so I could not hear anything.
okay, sorry. So this is our internal energy. Just check it.
How we get this?
Because this part is the numerator part,
Okay, yes,
correct? Just put it, we'll get this. Now, very different forms you know for these things. What are those forms? Um,
minus del ln q del beta. Yes, this is I.
if you use the form of our beta, then probably it is kbt square, you know, dln q dt.
Yes,
So these three forms are there, but till now we don't know beta is kbt. You can write it here. This. So this is the internal energy. But here minus sign will be there, I think, right?
yes,
Minus sign should be there. Here it will be not. Hmm. So next thing we will find out the pressure, like canonical ensemble. In canonical ensemble, what we have defined, if you remember, what was pressure? Pj was dej by dv, right?
yes,
Same thing we'll do here. So here we will, it instead of d, it is ej, it is, now how you can write it? It's pressure. So the ej, but the energy states are j is correct. Pressure means this is capital, no, probability is capital P, so it should be the capital P. Pressure is the small p, like this, or better to write it as K, it's J only, because it's EJ. So same formula we'll use. So PJ is minus del EJ del P. Okay.
yes,
So again, similarly, if we want to calculate the average pressure, that will function will be again beta, V and gamma. So it will be sum over K, sum over
this pressure
J,
will be pj or pkj.
PJ, 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 and PJ is the function of, no, volume, but it's okay. And it is probability of Kj, V, beta, and gamma. Okay, same thing, same treatment we have done for the energy. We will done the same thing. So here we will put volume is there as well. Okay, I think it's correct. Yes. Then what should we do? what we can write, because we need p we know, so we will invoke the expression of p here, so we can write it. Sorry, instead of pj we can write minus d ej dv. Actually pj is not function of volume even. It should not be, right? Or it should be, because you see ej is function of volume, but when you differentiate with volume it will not be function of volume anymore,
Yes.
right? But no, no.
Why?
Let's say x square is there, you differentiate with x,
Yes,
still
there will
you
be.
get 2x. No? It's not always true. If it is linear, ej is linear, let's say it's only x or 3x, 4x, 5x, then it will be constant. You don't know ej is linearly dependent on v or not. That you don't know. Okay. So from here, what you can write now, just see. You can do this. You have just multiplied one beta and in numerator and one denominator. Then you can
Yes.
write it. Okay, then you can write it. Minus sign is there. So it is 1 by j del v of this. Can we write it or not? Just break it. Then we can see. And n k is also function of volume. So it will be to the power beta ej one in gamma omega should not be there. It's
In the second term, there is one del nk del v.
del n k del v, but del n k del v is 1. You don't know that. If you just do the first one, let me check. This grand canonical part is not very available in books. So they generally say that, okay, you have done canonical, you can do grand canonical. Hmm. It's basically not in the derivative. I think. It should be like this. You see, if you do it, then what will you get? First, you have to differentiate with, it is del b, so it is del bj, it will be power minus b bj b and dbj. So then you can write it as minus beta e to the power d ub into bj. This is true. Okay, just check
Yes.
it. Check it. No. So minus sign will not be there now. So what you can write it in? So it can be written as 1 by beta, zeta. Oh, oh, one mistake we have done. Ah, see, it should be nk. How can be the function of v? Nk should not be the function of
Yes.
v, right? N is the number of
Yes.
particles. That is not function of v. Energy, obviously, because if you change the uh, volume of the macro state from which you have started, you have built out the ensemble, then obviously if you have different volume, energy distribution will different, that you know from kinetic theory of gas. But number of particle, how it can be changed? If volume
Number of particle will be
distribution,
same.
that is your also the prefactor. I mean, you have defined that. You have defined the volume, you have defined the number of particles. So number of particle and volume are the independent variables. EJ can be dependent on both, just like canonical ensemble. But number of particle and volume can't be dependent on each other. So that is the mistake here. NK is not the function of volume. By flow, we have written this. I have written this, sorry, not we, my mistake. So that's why they have taken it in. So it's just like a constant here. It's not dependent on volume. So in that case, you can write it. This you can now write it. So what is this?
Which thing?
This is
The grand canonical partition function total.
correct. So this is our pressure. You can take in to here, so we can write it then DLN. Constant things are beta and gamma. Just check what was in our in canonical ensemble. Is it matching or not?
Yes.
Matching, right? Instead of just xi, it is q.
Yes.
Great. Next. So we have done our internal energy. We have done our we have calculated our particles. Now what? Sorry, pressure. So now what should we do? I have seen all number of particle, right? This was not in our canonical ensemble part. It is totally new. N average. Function of V, beta, gamma. So similarly, it is only Nk, not function of volume, not anything. Then it is Pkj, V beta. And okay, you try it first. I will not do it. Then I will check. Can you do it?
Nk into pkj.
Hmm. Pkj is the probability, and Nk. It should be like this, no? What is our general
Yes.
form?
X into pj.
samovar.
Yes.
But here two variables are there. So kj will be there and p will be kj. Now it may be xk, it may be j, it may be xkj. You don't know. It can be anything. So we are following that. Just calculate it. Try to calculate it. It's not very difficult. Have 5 minutes. 5 minutes is more than enough. Just put the form of a probability, then you can easily do it.
Yes, I have put that.
Uh-huh. You follow the trend, you have to find out by which you have to make the differentiate the partition function. For energy average, you have make the derivative of partition function with respect to beta. Why? Because in a partition function, it is e to the power minus beta ej. So if you derivative it with the beta, then automatically ej will be come out. So here you have to take out the nk. So by which you have to take the derivative.
Gamma.
Exactly. Just do that. What is your answer?
Minus del xi del gamma.
Minus del xi del gamma. And in p factor, it is 1 by gamma, 1 by xi, right?
Yes.
Yes. So this is your answer. Let me do it. All right. This manipulation you have to do several times. Correct. So just check it correct or not. Okay,
Yes.
and this is our denominator numerator. So this minus you have not mentioned. You had you mentioned that?
Yes, I have mentioned.
Okay, fine. Or you can write it as,
Del ln xi del gamma.
or how you can write it, because you know gamma equal to mu by kbt. If you know,
Mu by kVt.
so if you know gamma equals to mu by kbt, then you can write it as,
KVt square by mu.
let us check how you can write it. So it is the derivative of what? Derivative of mu. So it should be equals to
Minus kVt will be. Yes, this will be 1 by kVt.
this will be right.
Yes.
This way also you can write it. Or
Entropy.
entropy. And that was the most difficult, because if you calculate entropy, then you can calculate anything now, because you have internal energy, you have the pressure, you have the number of particles in average. So if you know entropy, then easily you can calculate the enthalpy or our Gibbs energy or Helmholtz free energy, all three things. So we calculate the entropy. So same thing we'll do. We'll again define a function which is just ln of partition function, just done in our canonical ensemble. Same thing we will do here. So what you can so f will be function of also v beta and gamma, or you can write it as f is function of, right, same way, nothing is different.
Beta t and gamma mu.
But that you don't know right now.
Okay.
It's better to write beta and gamma. Here we have just say if you know it, then that we will figure out, because if you remember using these tricks while calculating this beta, the sorry entropy, you have figured out what is beta, correct?
Yes.
Beta you know, 1 by kbt. Beta you know, beta is the same beta. It means here you don't know, but you can guess it. If you done the same treatment here also, you will find out what will be beta and then what will be gamma. These two things you can figure it out. So from here, what will be df? Del f del beta, where gamma and
F
all
constant G
ej
gamma.
are fixed. These are partial derivative. And
Del F del EJ.
del ej when all other ej's are fixed. Correct?
EI not equal to J.
So let me write it k. No, k, not k. K is
EI
for
not
n.
equal to J.
Hmm. Okay.
Why it is not varying with the number of particles?
Number of particles. It's not
Yes,
function of number of particles. It's beta and gamma.
but entropy should vary with number of particles.
It is not entropy, it's just a function. ln of partition function.
Yes, but when we calculate the whole thing,
That we'll
then
see
there will be
later. That should become inherently. If,
okay.
if entropy is function of particle, then it should come automatically. We'll not invoke anything. Okay. So let us do step by step. So first term, so what will be this? What is ln? What is f? F is ln
Capital J,
but
jk
you have
e to
to
the power
write it.
minus beta ej into e to the power minus n gamma n.
So how you can now approach? Ln is there, right? Ln a plus ln b. So how you can write it? Okay, so let me write it as first. It should not be complicated. Ln, not gamma, sorry, xi. So now you can write it as like this,
Yes,
and this in, and you know the derivative and some commute, so you can take it here as well. But one thing we have done wrong. Can you figure out what thing we have done wrong?
the cross term.
Cross term. So you should not write here. If you write an EJ here, you have to choose different equation. J prime, let's say J prime, right? Dummy variable you have to use. You should use. Later it will be same, but still it should. Then a delta function will come here like this. Okay. Can you write it? Or we should use in K as well. No, in K it should not be. So it will be No, in K it should not be, I think. Hmm. So you can write it as minus, okay? I think, yes. Correct? Just checking.
Yes,
And what was our P?
1 by beta del L N Z del Z.
So P, capital P.
E to the power minus beta ij, e to the power minus gamma n k by capital Z, sum over kj.
Yes. This one, right?
Yes,
Hmm. It's not coming right. Okay, so, but it is, okay, okay. I think I have to understand. This K is also there. So that K should also be, okay, okay. Okay. Hmm. It's a good tricky part. You see that K is not, not means there is no K term here, right?
yes, that I was saying there.
Hmm. K part should be there, but our energy levels are EJ. Then EJ was actually, if you remember, EJ was actually sum over EJK like this,
Yes,
right? Or means AJ was sum over AJK like this.
yes,
So, so you have, it's better to use EJK. Means I'm explaining what I am writing here, then it will be easier to understand. Okay. Otherwise, you have to carry this part. You can write it as a probability. If you remove it, then only you can write it. Otherwise, you can't. Then you have to carry it. So to avoid that, it's better to use when other energy levels are, or those are constant. I let's do like this. So what I'm saying, let me explain it here. So should we carry it from the beginning? But here we have not mentioned that. We have choose only EJ. EJ was correct. There is nothing wrong with it. We have done nothing wrong. This is correct. Okay, it's correct. So we have to write it like this. We have done. Okay, let us write it. Now it's correct, right? We have to written like this because our states are EJ NK, not only EJ. If it is canonical, then only it was EJ, right? It is EJ
yes,
NK. If you see the
Number of particles also associated with the energy.
Means you have yes, this is the energy levels. See, energy levels are EJ, NK, EJ, NK. Eigenstates are EJ, NK, not only EJ. If you I have written EJ, but EJ is for canonical only. Okay. Like, that is not that is correct. But if I write eigenstate, then it is not only for with energy, it is also NK should be there, right? So it should be EJ NK like this. Okay, I think it's clear now.
Yes.
So you have to differentiate EJ NK with EJ NK, and here another you have to make constant. Let's say other energy levels EI or EJ prime NK prime not equals to EJ NK and beta and gamma. Okay, or in different ways also you can write it. Okay,
If I write it EJK,
no, that I don't want to write now. That I'm saying energy levels are EJ. This is one energy level that is EJ. That is not wrong. In these energy levels, there are other. This will again split. These are eigenstate. This is EJN1, EJN2, EJN3, and so on. So in general, EJNK. This is the general eigenstate. This is not the only energy levels. This is energy particle levels. You can see because all have the same energy, na. So you can't say this is the energy level. Can you get it?
yes, EJ is fixed.
EJ is same. This part I will discuss again. Just wait. No, this is confusing. I will discuss it after doing this calculation. Okay. So then, hmm, so how you can write it? It should be DEJNK. Okay, DEK. Okay, this you know, right? DFDXY means it's actually DXDY, right?
Yes.
This you know. I'm not writing it.
Which one is first and which one is second?
Does not matter.
For exact differential.
Hmm. Generally, you should follow the chronology. Is del EJ, del NK. Okay. So it is del EJ is there and del NK should be operate here actually. Correct?
Yes.
And again, we have to make this prime. It will be again, gamma term will be there, I think, yes. Hmm. So if gamma term is there, so it will be beta gamma. Minus minus will be plus. So it is beta gamma. It is minus gamma NK prime. And yes, now it's time. Gamma NK. It is beta gamma. So it can write it as beta gamma and then the probability. Oh, yes. Correct?
Yes.
Just check it. Just check it. Because the mistakes were there. No? So just check it. Okay, now we can proceed. So what we can now write?
Please lift it upward.
Okay, sorry.
Okay.
It's fine, right?
Yes.
So what will be our df now? Df has three terms. First term is clear. It is just derivative with respect to beta. So it is d ln partition function zeta by del beta. You know what is that? That is our E average minus E average, right?
Yes.
So it is just minus E average del beta. Next term is this gamma. So d ln xi of d gamma is our minus n average. And the last term is this is our beta gamma.
How can we say it is number average D gamma? Second term.
Just see what was our number average. This.
Yes.
Okay. And what is this?
Del ln Q del gamma. Sorry, del ln J del gamma.
So it's number average, no? Same
Yes.
thing. Minus. Only minus signs. So it is sum over j, k, sum over j. Then this part we have calculated. This part we have calculated. So it is actually beta gamma.
Yes.
So what you can write? Just check because in here from the materials I am writing, this gamma is not there actually because they have just include. You are saying that they have just done is a E J N K like this. That's why this N K was not differentiated. Only this beta came out, but that should not be the case.
Why it is?
That also I'm thinking. It should not be like that.
NK term should also be differentiable.
Hmm. If you want to, if you have dx dy and you have x square y square, then certainly it will be 2x 2y.
If we don't differentiate, then we have to write del xi del nk one term.
Hmm. No, we have surely differentiated. Otherwise, this part will not come.
Yes.
But in prefactor, they have only have this prefactor. Oh,
Then the gamma is not there.
hmm. Okay, let us check what we'll get.
It is only e to the power minus nk.
Hmm. That's that. Okay, let us check what we will get. Otherwise, I'll see where is the mistake. We are getting this, so we'll follow this. So, okay, in this way they have done this. Okay, you have to recognize this part. What is this part? This is they are saying, yeah, oh, okay. It's PDV or PDV. That you have to find it out from where. Key average. What was our key average? DV on it. Just let me check. The steps are not done actually. In between steps are not done. Hmm. In canonical ensemble, heat and work done from that part.
Yes,
So here also we have to do it. What is this part? That we have to recognize. Otherwise we can't proceed. This part we have to recognize. So just let me check how we have done this in our canonical part. Just we will follow this. Hmm. Here also they have, because in that case it was just PJ DEJ PJ DEJ beta PJ DEJ. It is not PJ. Okay. It's partition function. So KJ is there. So okay. KJ is the PJ. And this PJ DEJ was understood as the work done. Oh, that's the case. That we have done, right?
yes.
This thing here. Here we have done it.
The work done was D equal to sum over EJ DPJ plus PJ DEJ.
Yes, yes, here. So here also we have to do it. So what is our total work done? AJ
Sum over,
DEJ. Sum over AJ
yes, EJ
DEJ.
DEJ.
And from sum over AJ DEJ we have done this. Divided by 4 PJ DEJ. Okay, so let us check what we get here. So here our work done formula will be same. So work done will be this, right?
Yes. In AJ there is also K.
So now you can write it as this. Hmm. Okay. And then we have divided with the capital A, and then okay, just let me check. Not here. It will divided by capital A. then it will be is if you divide it by so average work done, then it will be PAJ DEJ. Okay, okay, the DEJ is there, but DNG is not there. So gamma into will be there. Okay, okay. So this part we have to check. Okay, for grand canonical, it's not very straightforward. In canonical, you know, because number of particle was not changing there. So easily you can do the work done, you can calculate it. But here for grand canonical, it's not very much straightforward to calculate. So we are assuming right now, I will see it, okay? I will see this part. They have written, this is actually, just I'm writing here, it is our, you can also try, okay? Just see the canonical part and do it. Try it, I will also try it, okay? This part will be minus PdV, this part, okay? If you do it, this is our main part, this will have, we have to check. P average you know, na? So from here you can do it, but you have to first solve it. I will also solve it. Is it clear what we have to do?
Yes.
Then rest of the part is easy. Plus plus.
ED beta.
Hmm. So in both ways you can add. Similarly, these things we have done in similar manner.
Why it's EDB?
No, not dv, d beta. This is right. Okay. And from thermodynamics, you know what you know, d plus q equals to,
DU plus PDB.
and now minus mu d, and you have to consider because particle flow is there.
Yes. I
Okay.
did not study this mu-dn part.
Okay. After gives to m part, you will study it. Minus mu dn will be there. Extra term will be added.
Yes, but that expression is on the DG expression.
From dg expression only.
Yes, 3dp plus SDT plus summation mu I dni.
And that will be added for all the same thing will be added for all observe for internal energy enthalpy for all cases.
Okay, then it's okay.
Okay. This actually beta PD. This we have to check. We have to prove it. Otherwise, this will be incomplete. Beta PDB. This we have to prove. So yes. So by comparing, we will get. We can now compare these two equations, right?
Yes.
So if you compare, then what we will get? We will get first is
In the last line of the D of this, fourth line from under.
this one,
Yes. What
this
is
line,
yes? What is before PDB?
beta. Now we can compare it.
One gamma was also there.
No, they are saying this is the beta PV.
With gamma, that total part is
What?
PDB.
Huh. I don't know they are correct or not, but they are saying because they did not have the gamma part. Now we have gamma, so we have to check whether we will get the same thing or we will have the gamma. That we have to check. That I'm saying, no? Maybe there is a gamma. I don't know, but
Okay.
should not be because you see here it's only p by 2. If gamma is also there, then beta gamma t square something will be there. That should not be expected. But one thing I'm saying is that so beta is actually one kb is missing. Okay, okay. Hmm. So what we can write, we can compare, but no, there is a trick. This is not ds. So from here, what you can write, let's say this actually kb is by kb. Huh. So it is, you can
Why
write
this is
here,
not DS?
just wait. Now you can compare.
Yes.
Now you can
Mu by
compare.
KBT is gamma.
Okay. So step by step we can do because beta is 1 by kbt. Till now we don't know. We have just written here, but till now we don't know. Because in previous case we have already done. We know it should be like this, so that's why we are assuming it. Because in our that part, in canonical part, we have done
Canonical
it.
error.
Uh, so, but here also we should follow the same. I'm not interested in canonical beta is 1 by kbt. That's okay, but here also you should get that, na? Individually, separately, independently. Canonical result. Because you don't know the canonical ensemble, that does not mean you can't solve the GAN canonical one. It should not be like that.
But canonical is the first step. It is the extension of this canonical ensemble.
That I know, but still. Hmm. Okay. Okay, now from here also you can independently show. Mhm. If you remember in canonical ensemble, we have split it in hit and work, and from there we have proved that beta equals to 1 by kT, correct?
Yes.
So here also you can do that. Here also you can do that. We have not done those steps, but here also you can do. But you don't know that is whether KB or not. That you don't know definitely. But you can prove it is a 1 by K2 definitely. And you know by using the by relating with the gas.
Yes, we can prove K equal to KB.
Yes, yes. By relating the gas equation, we have seen that that K is actually a K. So if you now compare, so it's clear that beta equals to 1 by kBt. You know this actually. By using this, you are comparing. PdV is correct and gamma is minus mu by kBt. Hmm. So gamma is not mu by kBt. Gamma is minus mu by kBt. And Ds is kb times d of f plus uh, beta del E, this. Okay. So from here you can write kb f. F is ln zeta plus beta del E. Beta del E means del E by kbt minus del n by mu kbt. So this is our S. Okay. Is it clear?
Yes.
Great. So this is our S. So let me just summarize. Then average is, or you can put it as. Okay. What is next? Pressure, right? What was pressure?
Minus del EJ del E.
This one. This one. So now 1 by beta is kBt. So you can directly write it. Comma. And last one is in particular H that we have also calculated. Okay, here we have not put it the minus.
Minus
So
1
minus.
by psi del gamma.
So minus sign should be there. So minus sign will be kBt dln. Great. Okay. So what left? You don't know what is this mu is. That you have to check.
Yes.
And also we have to, okay, we'll see one more interesting equation. Okay, just check if there is any doubt or not, then you can start after 2 minutes. Coming from washroom.
No doubt it is same as the previous. What is the symbol of microcanonical partition function?
The partition function is because it's just 1 by gamma, na? Then like this delta function. That's why.
Yes.
There is no
And for
distribution.
canonical, it's Q.
There is no distribution in case of microcanonical. So partition function is
All
meaningless.
are equally possible.
डिस्ट्रीब्यूशन ही नहीं है तो तुम किसके ऊपर शाम कुछ नहीं nothing is there.
Equal a
Yeah.
priori.
No, here is also equal a priori. For canonical and canonical also, all microstate are equally probable. But there is a distribution in terms of energy. In canonical, there is a distribution in terms of energy and number of particles. In microcanonical, no distribution is there. All states are same. So just one by all state, one by
Yes.
nothing is there. That's why. Okay. So you know this is our partition function, grand canonical partition function. Okay. So we can just see this part. Can I write it as QV?
Yes. Canonical partition function.
Not canonical because canonical it's NV, NV beta, so it's QV beta only. But I'm just renaming this part.
Yes.
Then you can write it like this. Okay. Now, so if you have the fixed n, then obviously it is the grand canonical. It will reduce to, you know these things. If the n is fixed, n is not varying, then obviously it's the summation will
Yes.
goes away. That's correct. So, and gamma, you know, so instead of gamma, you can write it mu by kb. Correct? Let defining lambda is e to the power mu by kb. Then it will be okay. It means that correct. Just check.
Yes.
No, it's not correct.
Yes. It is the expression.
It's not correct. It's actually mu lambda to the power n. Okay. Lambda is e to the power mu by kbt, na?
Yes. Lambda to the power n.
So in this way also you can write the grand canonical ensemble partition function. Now, if you remember in thermodynamics, how you define the chemical potential, mu I equals to kBT,
Del G
then
del Ni.
that's okay. In after that, LNAI, right?
KBT ln AI. Yes.
Activity. It's initial, it's final. In this way, mean ionic activity, these all things we have discussed also. And you calculated the daily as kBT ln AF by AI in this fashion.
Yes.
Correct? So here from this equation, if you want to calculate, then what we will get? Del mu will be kbt ln lambda I by lambda I.
Yes.
So it's clear that lambda is actually the activity, equivalent to
Yes.
activity, right? Right. So can write it as lambda is actually the activity, microscopic activity.
Why it is called microscopic activity?
Microscopic means I'm just saying because we are doing in the microscopic picture, na this mu, kbt, these things are nk sum over. That's why after taking average, you will get the original one. That's why even activity. Okay.
So the lambda average is the activity.
No, not like that, but still, because this is not the don't need to average, but this is related with NK, right? These things we have to take the average now. That's why.
Yes.
That's why I'm saying. Okay. So if you have written this, then you have find out lambda activity, and so what is G? You know, mu times N.
Yes.
Therefore, using this we will use later. We have again we know we have used this formula Ts equals to okay, let me write it clearly. G is this and G is again H minus Ts, and H is E plus PV minus Ts. So from here we can write Ts equals to
E plus PV minus mu n.
E plus PV minus mu n. Now in statistical sense, in microscopic sense, that's why I'm saying there. So we can write it as T S average equals to E average minus mu into N average plus P into V average, right?
Yes.
Hmm. But here we have already derived the equation. Why am this equation we know. This equation we know, right?
Yes.
So if we know, then TS from here, what will be the TS that we want to write? From here, the TS will be, if this is the S, this is our from thermodynamics, that's correct. From statistical thermodynamics, we can write that T S average is eventually K. I think I have done something wrong here. Just check. Yes, is this.
Everything is correct here.
No, this KB will be multiplied now. So this KB and this KB will be there.
We have divided the whole equation by kb.
No, no. AF is ln, sorry, AF is this multiplied by KB. That's why KB is here. Beta is 1 by KBT. And after multiplying KB, it should be only T.
Yes.
And here you are writing TS. That's is the case. So then it will be KBT is that is. So if you compare from here, you can write by comparing that PV is just KBT ln this. This is direct relation of grand canonical partition function. If you remember, in our canonical, Helmholtz free energy was like that: KBT ln Q minus KBT ln Q.
Yes, A equals to minus capital L into.
So canonical partition function is actually equivalent to Helmholtz free energy. KBT is the constant, ln is ln. So direct, if you want to relate our partition function to some physically observable quantity, physical quantity, then canonical partition function is actually the Helmholtz free energy. What we have defined canonical partition function, that is nothing but our Helmholtz free energy, correct?
Yes,
Here also, the grand canonical partition function is nothing but the PV work done. PV is the work done.
yes.
That's the case. Okay, now this is okay.
Any physical significance of this?
This is the physical significance, no? That this partition
Now,
function.
how work done is related with the number of particle change?
No, when you say the no, PV is not see, PdV is dW, right? That is a dW. PV is the total force like thing, P pressure into volume, like that. It is not dW. dW is PdV. That is the work done. Then we have to do external work. Then you see the energy level is changing or the population density is changing, those things.
Okay.
So what else? Some next. Now we know the entropy. So easily we can calculate the enthalpy. Del will be del E minus
E average minus T del S
no PdV.
plus PdV.
H is what? H is E plus
U
PV.
plus PV.
E then V is V plus P.
Yes, H is function of pressure.
So what we can write now? So del okay. E we know KB
Yes,
T square du ln.
del ln psi del T.
P we also know. Here we have written listed this. Correct? That
Yes,
is KBTV then DLN.
del V.
That's it. That is our internal energy. Sorry, Helmholtz free energy. And again, you can take common KB. Okay. What else gives free energy and Helmholtz free energy? Helmholtz free energy is U minus TS. So,
E average minus T into S average.
correct. So, TS average already we have written. So, TS average is this. So, E minus TS average. Just let me write. So, E minus TS average is what? KBT ln this. then minus E plus mu n. So E will cancel out. So it is mu n. See, in canonical part, only that mu n part will not there. Rest of the things is same.
Yes.
And G is H
H
minus
minus
Ts,
Ts.
correct? So H average is this E plus PV. So E plus EP and PS is KBT LNDs.
Minus
So
E
this,
average plus mu n average.
but this is actually PV average. Okay, I'm not putting average here, but generally it is PV average. Everything because this is S average, this is E average. That's why when you relate this S with S average, PV should be related with PV average. It's not
Yes.
in it's not V into P average. V into P average is different. This is this. It is PV average.
Yes, but when comes to Gibbs free energy, it will become V into P average.
Hmm. So, uh, okay, it's correct. So it is now TS minus E plus V. So everything you know now. A, B, T, ln this. Mu n also you know. You can put that expression. I'm not putting. This is our Gibbs free energy. Okay. Now we can put
Yes.
the n average, P average, this expression in terms of partition function. You know this. Okay. So let me stop here. I'm not discussing non-canonical ensemble mode. That part we will in next class discuss. This doubt part. I will see whether we should have it or different expression. That I will check. You should also check. Okay. Follow the
Okay.
canonical ensemble part and try to solve it. Then this issue I will solve in next class. After that we will discuss the assignment question, and from up next to next week we will discuss the mass theory and this part. Because this molecular part you already know. This part already we have discussed.
Yes.
So that is not that much important. We will discuss at the last class. In the last class. That is not that much important. That you can do. But this Mayer's theory or you are saying this cluster, I also don't know. Cluster info, information, what is that? I don't know. बिल्कुल पता नहीं. देखना पड़ेगा. So for that I need some time. That's why I'm saying next class I will do that numerical problems. You just send me all the assignments problem and other problems also you have doubt. Anything. Okay.
Okay.
Up to week 6 you should send. You just send it and I will see. Then next week we will let us finish it. Also this grand canonical this doubt that also I will finish. And just you go through this all uh, derivation of this grand canonical and the canonical part. Then I think it will be very clear because grand canonical part has not done detail in books. Really, I don't know nowadays, but when we studied, it was not. It's there, but in detail, it's not there. Step by step, you have it's not detailed. In between step, the missing links you have to fill it by your own. That I have tried. Okay, and fluctuation just left. If time permits in next class after doing this fluctuation, then after doing the numerical problems, I will just discuss this. Like it will hardly take 30 minutes. Fluctuation parts in canonical ensemble, it was 1 by n to the power. If you remember, n to the power half. So it's very huge fluctuation.
Yes.
So you can deal with the average value. Here also you'll see that fluctuation. The fluctuation part I will just discuss. Then it will be totally complete. Okay, I think so. Okay, so do you have any other doubt or any doubt regarding this class?
No,
I think it's understandable. Some in some point it was some mistakes are there, but okay, ultimately we have managed it.
I will practice this once more.
And if you find uh anything wrong there, then just say me. Okay,
Okay,
and try to solve that this part. I will also solve this part. Whether that gamma should be there or not, that we have to check. And if gamma
okay,
is there, then what will be the rest of derivation? That is correct. Otherwise, we have to follow that formal derivation they done in this note actually. That I will check. That I will check. Okay, so let me stop the screen sharing first. Where is it? Okay, so do it and send me those. And I think that PDF I have sent to you, right? Any PDF left?
the exam those.
Okay, you should inform me. I forgot it totally. Okay, I'll do it. And those and these books, just give me a reminder. Okay, tomorrow, just give me a
Okay,
reminder.
and
Okay,
please upload these notes today. I will practice it.
I will upload it. I will upload it.
This
Total.
PDF.
This PDF or totally I will upload it. And that demand Bagji's book and that exam notes I will arrange. In next class, you also just send me the assignment problems and we'll do it in the next
From
class.
week 1 to week 6.
Week 1 to week 6, yes. That we will solve.
Okay, thank you.
Okay. So thanks for joining again. Uh, we'll meet next Sunday. Next Sunday from 4 to 6. Okay. Then after that we'll start those things. Don't worry. Okay. So thank you very much for joining. Again, we'll meet in the next class.